of loops. Now, unlike other programming languages, Go only has one loop. This is for loop. We don't have while loop, we don't have do while loop, we don't have any other those loops, because the for loop is semantics. By changing the syntax of the for loop a little, we can implement all those patterns. Now, how does a loop work? By the way, a loop just means executing a set of instructions again and again until a specified limit in order to reduce the boilerplate code. Instead of writing these statements again and again until like 10 times, we can use the construct of loops, which is available in every programming language, to run this same statement 10 times. Okay, so how does this loop work in Go? We are here declaring a variable of sum, a variable named sum, which is of type integer. If you hover over it, it will say integer because the initializing statement is 0. Now we are initializing a variable named sum. Now this is how the loop works. The first statement is the initializer statement. It is some kind of expression. So here we are initializing a variable called I, and I is only usable inside these curly braces. It is only usable inside this scope. This is called lexical scope, and I only works inside this. And after every iteration, I's value changes. A new instance of I is created. Okay, the previous instance is destroyed. Now, this is the first expression that is that runs with every iteration. Second, the iteration, the whatever statement inside the loop construct, this is executed. After the execution, this statement runs. We change the value of I. We increment the value of I. Then at the end, we check this condition, whether this condition is true or false. If this condition is false, then we break out of this loop. If this condition is true, then we again continue with this, then we execute this, then we execute this, then we check this, then we execute this. So this is how this cycle of a typical for loop. Okay. Now to visualize it, what we can do is we can use a debugger. So if we add a breakpoint here, so a debugger basically means you can investigate the flow of the program using this tool called debugger to better understand how the program works, to investigate the flow of the program basically. Now if we run this, VS Code has a inbuilt debugger for Go. Now we can run this, and in first iteration we have I with value 0 and we have sum with value 0. We have a breakpoint here. The program stopped here at the first iteration. Now using this, we can go to the second iteration. So after I click this, we came outside this loop, and here we are checking whether I's value is smaller than 10 or not. Since I's value is 1 after the first iteration, the condition is true. That's why the loop runs again. And if we click on this, now I's value is 1 at this point, because in the previous iteration, I's value was incremented to from 0 to 1 after the end of this statement. Now, since you're entering this loop again, now I's value is 1. After this, I's value will be 2. If we click on this, at this point, I's value is 2 and the condition is still true. So now we come inside the loop again. Now sum's value was 1. When you click on this, I's value is 2. When you click on this, sum's value gets to 3. And this is how the loop works. Every time the iteration runs, the increment happens, the conditions checks, and if it's still true, then it progresses. It proceeds to the next iteration. And this is the way we have 7, we have 8, and we have 9. And at this point, I's value is 10. So in the next statement, the loop will break and we will reach the end statement. So we'll break out of this loop and we'll reach the end of the main function. And after this, the value will print. And so that's how a for loop, a typical for loop works in Go. Now, if you want to implement the while loop from other programming languages, we can just get rid of the first two expressions, the initialization and the increment, the expression, and then we'll end up with a while loop, which basically has a for statement and a condition and the execution statements. So this is how you do while loop in Go. So if we run this, we have 1024 is the sum. So until this condition is true, this loop will keep running. And once this condition is false, it will break out of this loop and we'll see the print statement. And at this point, what if we take out the condition? If we take out the condition, and what if we run this? At this point, our program is stuck in an infinite loop. An infinite loop basically means because there was no condition to break out of this loop, our program never exits and it is stuck inside the same set of calculations. So unless you have a specific condition at this step, the program will never exit. The program will never exit out of this loop unless there is an explicit break statement here. So at this case, let's stop this execution. And here, what if we add a condition? So we have not seen if conditions yet, but if add a condition, if sum is greater than 100, then we break. We add a condition here for breaking out of this loop if the value of sum goes out of 100. And now if we run this, you can see that once the program reached 128, into the next iteration, the condition was true and it broke out of this loop. Now this pattern, if you're wondering why do we need infinite loops in the first place, since it hangs the program, we have some patterns, especially when we get to the concurrency chapters. There we have some patterns where we are constantly listening for signals from different Go routines and all. There we use this pattern of infinite loops. So we keep listening for signals and all. And the moment we get some signal, we break out of this loop. That's how this pattern works. So you should know that we have a way of implementing infinite loop, which is not always bad. There are uses for infinite loop also. Now it is a very good point to show if conditions. It is pretty simple to wrap your head around. We have a condition which starts with if, and whatever the condition that is provided after that, there is no braces. You have provided a condition which should evaluate to either true or false. And if it is true, then this statement will run. Otherwise, it won't. That's pretty much all there is to if condition. In the same way, in the for loop, in the first part, we could assign, we could initialize a variable, we could call an expression in the first part, in the first semicolon here, for here, this part. In the same way, in the if statement also, in the first part, we can initialize or we can call an expression in the first part. This variable v will be valid in the if condition, will be valid in the if lexical block. So for example, if we try to access v here, we try to see, let's say k equals to v. Now if we hover over it, it says undefined v because v was initialized in this if block in the first statement, and it is only valid inside this lexical block. It is not valid outside. So it is a very nice way of initializing and checking errors that we use with this feature of if. It reduces some amount of boilerplate load because of this pattern. We can initialize a variable and we can check a condition. And if that condition is true, then we get inside the if block. If not, then this is not executed. So this is a very nice way to reduce boilerplate code. The same way, after if, we can also use else. If this expression is evaluated and if this condition is true, then we get inside if block. If this condition is false, then we get to the else block and this part is executed. And as I said, the value of v is only available inside the if block and inside the else block. We cannot use the value of v outside the if and else block. And now I think it's a good time to take a look at some examples in the real world of how we use for and how we use if conditions and if else conditions. Here we can see they are looping over the number of CPUs and doing something. It does not matter what they are doing. And this is how people use for loops. And here you can see they're dynamically taking the length of this variable and initializing this loop and running these executions. Okay, this is how for loops work. And let's look at if. And this is how typical if, else if, and else conditions work. This is basic programming stuff. If this condition is true, then this part is run, or if this condition is true, then this part is run. Otherwise, if there is an else condition, that is run, or the program just keeps executing. Typical if else behaviors that we have in other programming languages. Nothing too special here or nothing to remember here. Go also has a switch case. In the first part, you can evaluate some expression, and this variable is available throughout the scope of this switch block. It is not available outside it. Now, using this, you initialize this variable using runtime.go operating system, this environment variable that is available to your Go programs by default. And you use this variable as a condition. You are checking, check the value of OS, this variable, and you are checking different values. Whether the value of this variable is this string, Darwin, or if the value of this variable is Linux, or if none of these cases satisfy, then it reaches the default block and this block gets executed. Otherwise, if one of these statements are true, if one of these cases are true, then that part gets executed and this breaks. It does not proceed further. It breaks out of this switch statement. And if we try to run this, we are getting Go runs on OS X because this matches our Go operating system. This environment matches Darwin. And that's why we are getting this. And the moment it matched this case, we came inside this block and this statement got executed and it broke out of this switch statement. Okay, this is the typical behavior of switch statements. Now this is another example of a switch case. A switch case condition can also be an expression. It can be a constant string, it can be a number, or it can also be an expression. If this will get evaluated, and depending on that, we'll get inside any of these blocks. And the moment any of the case statements are true, we get inside that block and the statements are executed and we break out of that loop. And if we try to run this, since today is Saturday, we'll probably get today. When is Saturday? It prints today because we came inside this block. There is another pattern with switch, which is a replacement for writing these kind of code. Let's say if we have if condition and we are checking something, then we have the block, then you have else if. When you are checking something, then you have another block, then you have another else if. We are checking something, we have another block, then at the end we have else. So instead of writing like this, we have this construct in a switch statement. So we can initialize a switch statement without any condition or without any expression. We just start with a curly braces with an empty switch. And now this is like an if else block. So this is an if condition. You can imagine this is another else if and this is an else condition. So this condition is checked from top to bottom. The moment one of the conditions are true, that block is executed. It comes out of the switch statement. If none of them do, then the default one is executed. So if we try to run this, we get good afternoon because it's not 5 yet when I'm recording this. Now we have a very interesting concept which is called defer. And this is very unique to the language Go, and other programming languages might have different implementation of the same concept, but in Go, we call this defer. Why do we use this concept? The defer concept is, before that, let's just execute this function. And we get, first, this is printed, the hello part, and then this is printed. What exactly is happening here is, the moment you use the keyword defer, and then you provide some expression. It can be a function call, it can be an expression, whatever. Whatever is provided in this part, this gets stacked in, let's say, some kind of stack. So we have a stack here, and this is pushed here. So this world, this instruction of print world, this stack is pushed here. And then this expression is pushed into the stack and the program starts to execute normally. Whatever instructions that come after it, they are run sequentially, however you can expect your program to run. So that's why after this evaluation, it did not print yet. This does not get executed yet. It is just evaluated and pushed into a stack. Now we reach at this stage and this is printed here. You can see the first hello. Now after this, the main program is finished. There are no more statements to run. At this point, the main function returns. We call this the main function returns. At this point, what the Go programming language does is it takes the stack and it starts to call all these functions, call all these expressions that were provided throughout the function execution, all the defer statements. There can have multiple defer statement in a function, and all the defer statements are pushed into the stack one by one, and the Go program starts to call them in that order by popping them off the stack. So that's why after the function return, after all the statements were executed, we see this getting executed, the println to world. So the first world hello is printed and then the world is printed. Now to understand this concept of differs and the stack of differ a little better, we have a loop. And in this loop, what we are doing, we are calling differ multiple times. Let's say 10 times. We are calling the differ statements 10 times in this for loop. And let's just execute it and then we'll understand what happened here. So say go run main.go, and you can see first the counting got printed, then we have done, then we have 9, 8, 7, 6, 5 in the reverse order. Now let's understand what exactly happened here. Okay, minimize this. First thing, the first statement in the function counting. First we saw this got printed in the console. Okay, this is done. Then we reach here in the for loop. With each iteration, let's say now we have a stack here. You have a stack where the Go programming language pushes all the differ statements, the call of all the differ statements. So in the first iteration, the i's value is 0 and we call differ. So this function, this expression is pushed into the stack. So we have print 0 here. Okay, this instruction is pushed into the stack. Second iteration, zeros, the i's value is 1. Now print 1 is pushed here. Then 2, then 3, then 4, then 5, then 6, 7, 8, 9. 7, 8, 9. Okay. And at this point, this statement, the for loop statement, the condition is false and it breaks out of the loop. And we reach here. At this point, counting, after printing counting, we see done getting printed here. Okay. And then there are no more statements in the program to execute. At this point, the main function returns. And when returning, the Go programming language runs all the deferred statements of that function. It runs all the deferred statements of that function when returning from the function. So at this point, what it does is it pops out of the stack. Since it's a stack, we push all the values on top of each other. It pops in that order. So that's why after seeing counting, then done, we see 9 getting printed, then 8, 7, 6, 5, 4, 3, 2, 1, 0. In the reverse order, all of them getting printed because the Go programming language pops all the elements from the stack in the order they were pushed. Now you should have a good idea of how differ works. Differ is basically pushing the execution of some function calls, some expression into a temporary stack. And when the function returns, the Go programming language executes all the functions. Now the question is why? Why do we need differs? Like, what are the use cases? Why would we need to execute statements before returning of the function? Why not execute them explicitly? Why not just execute them here? Now there are two answers to that. One is sometimes it is easy to forget running some statements in when we are developing, when we are writing code. For example, when we are opening a file. So since Go is a systems programming language, we have constructs to open files and read data from different sources. Now, after you open a file, you have to explicitly close the file. Otherwise, there will be memory leaks and your program will eat a lot of memory because there will be a lot of open files in case you are reading a lot of files in a for loop. In that case, every time you open a file, you have to explicitly close it. So what happens? You open the file. Let's say I write in pseudocode. You open the file, and at the end of executing all your complex calculations, you have to remember to call close on that file, on that function. Now there are two things that can happen here. Either as a human error, you can forget to close the file. That is a very expected scenario. A lot of times there are a lot of human errors in a program and we can forget, and we do forget. And it can be a file also, or it can be a database connection that we need to explicitly close while we are returning from the program. Otherwise memory leak happens. There are a lot of instances where after you start something, you have to explicitly stop it. The start and stop comes sequentially. The stop is mandatory. In these scenarios, you have to remember calling the close functionality. So either you can forget it, or during the execution of the program is broken. The program throws error. It panics. To talk in Go's terminology, it panics. We have not explored what is a panic yet, but panic basically means Go's way of throwing an exception. Go does not have the concept of exception where the flow of the program completely changes, but you can think of it as an exception. It throws an error and the program stops executing. That is basically a panic. Exactly what the name sounds like. So let's say you opened the file or you opened the database connections. You were running some instructions here. You are running some business logic. And at some point before you called close, at some point your program panicked. It threw some error, it panicked. And instead of going in this flow and calling close at the end, it panicked and it stopped the flow of the execution and it directly took this path. Now you never got to call close because in your mind, the way you had imagined it was, you'll open the file and you'll run some instructions and in the end you'll close it. Now you remembered to close it, but since your program panicked, since your program threw some error and returned from that statement, you never got to close the file. And all these database connections and all these open files are still there in the memory. Now you have a memory leak problem in your app. So for these use cases, the Go programming language has given the feature of defer. Now you don't have to remember to close the files, to close the database connection at the end of your function. Okay. What you can do is you can open the connection, open, let's say, file. And in the next line, what you can do, you can say defer close file. Now it won't instantly close the file because as you saw, the function is not called instantly when you call it using defer. It is evaluated and it is pushed into a stack. So the moment an error occurs at some point here, the Go programming language is configured in a way that the moment an error occurs, it starts executing all the functions that were in the defer stack, It starts popping all these functions and it starts executing them. That is a construct provided by the Go language itself. So for that functionality, for that feature of, in case of a panic, you still want to execute these statements. You still want to close a file in case of an error. In case of a panic, you still want to close your database connections in case of a panic. For this use case, we can use defer. And it's also readable. You are opening a file and you're instantly deferring the closing of file. So it does not matter what happens after a few hundreds lines of codes. The closing of file will always happen because of the way Go is built. The defer functions are always executed when the function returns. It does not matter it is successful or it panics. We can take a look at some examples of how people use differ in the real world. So if you search for differ here, you can see some functions where, as you can see, people are setting some database, and in the next line only they are calling differ. So that after, so this is a test in Go for your information. Don't have to worry about what all these are, but this is a test. Initially they are starting some database connection, and in the next line only they are deferring the teardown, basically the closing of the database connection, so that during the flow of this test, it does not matter it errors out or not, this closing of database connection is always executed and is also readable, that you started the database connection here and you close the connection in the next line. So after all these executions, the Go program runs this part, the differ, the teardown of the database. Okay, and you'll find a lot of differs in this project, which have different meanings in different contexts, but you should have a good idea by now. But what differ means? Basically pushing the execution of a function to the last statement, and ensuring that it always runs, does not matter the function is successful or errors out or not. Okay, that's all about differs. It is a very important concept and we'll use it a lot. Not a lot, but we'll use it quite frequently, and we should remember this pattern. Now we are in the territory of reference types. As I had mentioned earlier, Go has around 5 types of reference types. We have pointers, we have slices, we have functions, and we have channels, we have maps. We have 5 reference types. Reference types basically means they don't have the data themselves. They refer to some other data type. They depend on the different data type that works in the background to have the data. They don't have the data for themselves. Okay, so for now, let's explore pointers. Good. Now, Go has this concept called pointers, using which you can access the address of the variable. And what do we mean by address? Now, throughout the execution of the program, you assign different variables. You create different data types and you assign variables where you store those data types. Now, all those data types, all those variables are stored somewhere in the memory. Let's say this is your memory. There are different slots. You can think of them as slots. So when you create a variable, they are given some slot in your memory, in your random access memory, in your main memory, and they are given some slot, and that slot will have an address. It won't be a physical address because we are abstracted out from the core operating system kernel using the Go runtime. We are executing using the Go runtime. So we are given some address. It's a virtual address. Still, it is some kind of address. We can think of it as a physical address, but it's actually not. So that slot will have some address, and using this address, we use our variables. Our variables are stored in these slots. So what pointers do, using this data type called pointer, this data type stores the address of this variable. If we use a address of this variable, and we can access the address using this symbol, the AND symbol. And if we have a pointer, we can use the star symbol to find the value of that pointer that this points to. So this is all different terminologies. So let's see an example to understand how it all works. Now here we declare 2 variables, this I and j, with 42 and 2701. And we declare a new variable called p, which takes the address of I, because it uses this operator called AND. It takes the address of I and it assigns it to p. Now, if we hover over p, it says star integer, which basically means it is a pointer to an integer. It is not an integer value itself. It is of type pointer, but the pointer points to a value which is of type integer. That's what this means. Okay, and at the next statement, what we do, we print the value of p. Now p is a pointer type. P is not a value type. We cannot print the value of p directly. If you do print it, it will print some random garbage value because it is the address. Now we can print the value the pointer points to using this star operator. So this star operator is used to dereference. The terminology here is dereferencing a pointer, and we can do that using this star operator. So we can get the value of p using this star and we can print it. The next step, what we are doing here is we are taking some value, in this case 21, we are assigning it to this pointer, and we are assigning it to the value of the pointer. And since we have the address, since in this slot using the pointer we have the address of the variable, we can change the content of the value, the content of the address using this structure. You can do star p equals to 21. Now this address points to a different value, this 21. And when we print this, print I, now instead of 42 it will print 21, because using a pointer to I, using a pointer p to I, we change the value of I from 42 to 21 using a pointer. Now if p was not a pointer, if p was direct assignment, if we did p equals to I, then in that case, if we change the value of p, it would not have shown in the value of I. Since we used the pointer to I, when we modified the value of p, it also modified the value of I, because now both of them point to the same thing. Okay. The next step, we assign the address of j, and we are dividing this value and assigning it to the p, and now the j's value is also changed. And let's run this program and see whether it works expectedly or not. So if we do go run main.go, we get 3 values for 3 print statements. So what happened here? In the first print statement, i's value was 42 because we have not changed it yet. So that's why it printed 42. In the second print statement, we changed the value of I using the pointer p and we made it 21. That's why we see 21. Same way, here j's initial value was 2701, but after we did this thing, we did some calculation and assigned it to p. And since p was pointing to the address of j using this pointer operator, that's why the value of j is now 73, the result of this calculation. So that's what pointers are. They basically contain a data type which is an address of some variable, and using pointers you can change the content of that variable, whatever it points to. Now there are a lot of concepts in Go related to pointers. We will see it pretty frequently in a lot of different scenarios and a lot of different contexts. So for now, this information, this knowledge is pretty enough, and we'll see what else we can learn about pointers when we add more stuff, more basics to our knowledge of Go. So in the next phase, now let's look at what are structs. So struct is one of the data types of aggregate types. We have 2 types of aggregate types. One is array and the second one is struct. Array is a collection of similar data types, and a struct is a collection of different data types. So this is how a struct looks like. You say type because struct is a Go's native type. It's a type, the name of the struct, and you literally write the keyword struct, and then you open a curly braces and you write different data types. You define what are the types of these fields. These are the fields of the structs x and y, and beside them you write what are the types of those fields. Okay, and how do you use this struct? How do you initialize this struct? Here, if you see, you write the name of the struct, and in the curly braces you provide the values for these fields in that order, in the order that they were defined. Okay, now we write 1 and 2, and 1 will be assigned to x, 2 will be assigned to y, and since these are integers, we don't see an error. This satisfies these 2 literals that we are providing. These satisfy the condition that x is an integer, y is an integer, and we are assigning them to a struct which is called vertex. And now we can print this. We print it, go run main.go, we get this representation, string representation of struct, which is 1 and 2. There are also other things that we can do with a struct, which is, let's say we initialize a variable and we initialize this struct with x is 1 and y is 2. Now we can access the fields of this struct. The struct has two fields, which is x and y. We can access the fields using this dot operator. We can say whatever the variable is which we initialize the struct with, we can do v dot, and we can use x or y because those are the fields of the struct. And we can also assign some values to the struct. Even though we initialized with value 1 for the field x, we can change the value of x in the next statement, v dot x equals to 4. And now if we print v dot x, it will print 4 instead of 1. Now let's look at how pointers and structs work together, because this is very important. This is something that we'll use a lot when we are building projects. Now what we are doing here is we are initializing a struct with value x as 1 and y as 2, and we are assigning it to v. And in the next statement, we are initializing another variable with name p, and we are assigning the address of v, the address of this initialized struct, and we are assigning to p. Now here what we did is, using this pointer, we changed the value of x. Instead of 1, we made it this number. Okay. And what happens when we print v here? Let's print it and see what happens. Now we get this number, which is basically 10 to the power 9. We have 9 zeros here. Now that's the point. If we use a pointer and if we have a pointer to a struct, and using that, we can change the values of the fields of the struct using a pointer to a struct. This concept is something that we will use a lot when we're actually building real world stuff. In this example, we are just looking at different variation of defining a struct and different variation of initializing structs. First, run this example, and then we'll see what's happening here. Okay. Now, in the previous example, we had written it. We had written the fields this way. We had written x integer, and then we have written y as integer. Instead of doing this, since both these fields have the same type, both of these fields are integers, we can put them in the same line. We can do x comma y integer. Now this is one variation of declaring a struct. Okay. Then let's come to initialization. What are the different types you can initialize a struct? This is one type that we have already seen. You can write the name of the struct, and you can provide the fields in that order. So 1 will be assigned to x, 2 will be assigned to y. And this is one way of initializing struct. The second way is you write the name of the struct, and you can provide a key value pairs. You can write the name of the field, in this case x, and you can provide a value. And then with comma, you can provide another value of I, y, and colon 2. You can do it like this. If you don't provide an explicit value for a field, by default, since Go has this concept of zero value initialization, by default, Go will assign the zero value of that data type. In this case, since it is an integer, Go will assign the value 0 to y. Does not matter whether you provided an explicit initialization value for y or not. Go will assign the value 0 to y. That is one way of initializing struct. Another way, what if you don't provide any fields? Just type the name of the struct and you initialize it. In this case, Go will assign the 0 value of both the fields to them. In this case, both of these fields are integers. So x will have 0 and y will have 0. Then you can also do this. This is struct literal syntax. And what this means is, this is kind of similar to this, but instead of providing the type vertex, P will have the provide pointer to vertex. And if you hover over it, v1 is a type vertex. If you look at it, v1 is a type vertex, but P has a type star vertex, which means P is a pointer which points to a struct which has the type vertex. It is a pointer to a struct. Okay. And that's why when we printed for v1, we got the result 1, 2. For P, we got the result 1, 2, which is a pointer, that's why this ampersand, the symbol and stands for. Then for v2 and v3, we have 1, 0, because here we only initialize x with the value 1. and the y was initialized with the 0 value. That's why we have 1 0. And in this case, we did not initialize any of the fields. That's why x has 0, y has 0. Now to wrap our heads around where do we actually use structs, we can look at a few examples of our open source repository. Let's search for the keyword struct here. Now structs are something, if you are a backend engineer or any kind of Go engineer, any kind of engineer, and you are using the Go programming language, structs are something you'll use a lot. Your day-to-day life will involve dealing with a lot of structs because it is a very versatile data structure and very commonly used data structure. If you get some JSON from front end, you have to parse it and store it into a struct before you can use it in your Go program. Because unlike JavaScript, you cannot use a JSON directly with your JavaScript object. Okay, you have to parse the JSON into a Go struct and then you can use the struct. That is one use case of structs. Okay, now let's look at some examples. We'll just skim through them to get a feel of how people are using structs. Okay, so this is one struct which has a field called plan ID and is of type string, and these are called struct tags. And what it says is the key is JSON and the value is plan ID. And it is a bit out of scope for now, but this basically means, let's say from the front end, from the client, we receive a JSON. We receive a JSON with this value, say plan ID as 3. Okay, this is the JSON we receive from front end. So when we are trying to read it in our handler, okay, first we have to do is you have to take this request body and we have to parse it. We have to unmarshal it into a Go struct before we can use it. We cannot use it directly because it's a JSON type and it is in bytes. When we are parsing it, we can use a struct like this, which has a field, a struct field with Go's own convention. And here we are saying that we are using this struct and any JSON field with the key plan ID will be parsed into this field, this plan ID. So using these tags, these are called struct tags, and with the key JSON, these tags are one way of mapping JSON fields to our own Go's struct fields, because the naming will be different. In Go, we'll have camel case fields, and the styling of Go is a little different than what we follow in typical JSON based payloads. That's why we have struct tags, so that we can map the JSON keys into our own struct fields. So that is something a little out of context now, but something useful to remember for now. This is what a typical struct looks like, and we have more examples of structs. We have this one, invite users. There's a string and there's an array. There's a slice. We have not explored slices yet, and there are a lot of examples of structs in this code base. You can notice it. First we have field names, then you have type, and you have tags. Depending on which application, which package is using it, we'll have different tags for a struct for different parsing mechanisms. Okay, so as you can see, structs are pretty versatile. We can store any type of data inside them. It does not matter what type is. In array, we can only store homogeneous data. In structs, we can store heterogeneous data. It can be an integer, it can be a string, it can be a slice, it can be a map, it can be anything. It can be pointers. Okay, so structs are very useful and something we'll use a lot. And this basics is enough to get us started with structs. Now, another thing about structs that I want to mention here is the capitalizing of the first character of the fields. And as you can see here, all the fields start with capital letters. And this is not a styling thing. This has a use case, as we have seen before. Capitalizing of fields and variables in a package in Go results in that variable or that type being exposed to code outside of that package. So for example, in this, we have this package called CMD, and this is another package called some test package. If we see the name here, and the package name is API v1 test. These two are different packages. Now, this package is using code from another package, from the CMD package. and it is using this struct, and it is importing that struct into this package so that it can initialize a new instance of it. What happens if we change this field from a capital R to small r? Let's change it and let's see what happens. And the moment we made it small case, as you can see, there are errors everywhere in the program, especially in those scenarios where we were accessing the field, this particular field of this struct that we were importing from another package. So that's the use of the capitalizing. If the first letter of that field of a struct is not capitalized, then we cannot access that field outside of that package. That's why we capitalize fields of a struct. And then we have arrays. As I said, arrays are a collection of same type of data types. Okay, that is the one-line explanation of arrays. So what we are doing here, we are declaring an array which has this type. It is a string and it can have 2 items. So this part, this 2 part, this is basically the size of the array. So when we say toString, when we say this, we mean this array is of type 2 items string. This size is the type of the array also. So this size is part of its type. So this array and this array, 3 string, these are of not the same types because it is of size 3 and it is of size 2. So that is one thing to remember. The size of the array is part of its type. Okay, next, what we are doing here, we are declaring a variable which is an array of length 2 of strings. And in the first index, we are storing the string hello. In the second index, we are storing the string world. We can access the indexes of the array using this syntax. The square brackets, and inside is the index number. And then we can print it, the index 0, the index 1. We can also print the whole array. The same way, instead of doing it like this, instead of declaring it here and initializing it this way, all the indexes, we can also use this syntax. What this syntax is, we can write the size of the array and we can write the type of the array. In this case, it is an integer of length 6. Then we can provide all the values in this order. 0, the index 0 will have 2, index 1 will have 3, index 2 will have 5, and so on. And we can print this. And let's run this. And as you can see, we have all the expected results. Now the 2 major points here are, 1, Go is a statically typed language, and second, an array size is part of its type. Now since we have these two facts, now arrays cannot be resized because the size of an array is part of its type. You cannot resize an array. You cannot reduce the size of an array. You cannot append to an array. You cannot do any of those things. An array is just a constant that whatever value you initialize it with or whatever value you push to it, and that size will always be the same. You can only push up to whatever value you initialize with. Arrays cannot be resized, and that is the reason you will not see arrays being used as frequently in real world systems. We will still use it when we have a fixed number of elements that we know the value of beforehand. But in most cases, we use another data structure provided